Okay, this section is on rose curves and spirals, and we played around with rose curves just for fun last class, so hopefully you remember doing that, and all of those graphs that we were just messing with were rose curves. Before we get into this, I want to review a little bit of what we looked at last class so that we can remember overall what we're looking at. So we're looking at different polar functions, and we looked at a few different ways to represent circles with polar functions last class. So the first most basic one we looked at was a function in the form of r equals 3. And we eventually realized that must just be a circle of radius 3. So anything in the form of r equals a, where a is just some positive integer, you've got a circle. The two other circles that we saw through graphing by hand on the 8-2, 8-3 notes either looked like r equals some number times the sine of theta, or r equals some number times cosine theta. So those are the two different, the three different representations of circle functions for polar. And after that, then we graphed another equation that looked like this. R equals, 1 plus 3 sine theta and I asked you guys, do you think that will be a circle or not? And we ended up seeing that that was actually a function, a graph that looked like this, something like that, and that is called a limicon. So any equation that looks like that, meaning something that looks like some number plus some other number times sine or cosine theta. So that we saw was a limicon. So those are the only two types of polar graphs that we looked at so far. Today we're going to look at rose curves and spirals. And each of these different types, so circles, limicons, circles all look a certain way. Limicons look like this, a number plus some number times sine or cosine theta. We're going to see the same thing with rose curves and spirals. Their equations always look a similar way and tell us specific information about the graph. The first thing you're going to want to do is pay attention to this information right here. So go ahead and grab your graphing calculator. You will need that for this section, and go hit the mode button and make sure that your mode, when you select mode and go down a few lines, you should be selected, you should have radians selected, and then the next line you should have polar selected. And then when this says format right here, there's a button on your calculator, the zoom button. If you look right above your zoom button on that top row, you should see a blue format, and so hit second format. In the very top line, you should move over and select polar GC instead of rectangular GC. And then you're going to need to make sure your window is ready to view these graphs as well. So hit window on that top row as well. Your theta min is 0, theta max is 2 pi, and then theta step, just type in pi divided by 24, and it will convert it to a decimal, but that's fine. Continue down another line, and we're going to make our x min -3 and the max 3 with a step of 1. And the y's will go -3 to 3 also with a step of 1. Once you do all of that, you're good to go for the rest of this section. Just make sure that you hit zoom 5 every time you want to view the graph. That way it's nice and square so that it's an accurate picture of the graph. Okay, so let's see what these functions look like. So go ahead and type in this first one on 1a, r equals 2 sine theta. So go to your y equals, type in sine of 2 theta, and then your window and mode should be all set. So after that, all you have to do, is hit zoom 5. And let's sketch a graph of what we've got. So we've got a little tiny flower, it looks like, with 4 petals. So I'm going to label my axes, and these are just sketches. You don't have to be too perfect here, but do your best to draw this sketch. It's sine of 2 theta. We've got 4 petals, so those leaves, if you will, are called petals. And it looks something like that. That's a horrible picture, but you get the idea from your calculator. And that is what we call a rose curve, even though they don't look like roses. We're going to be seeing in this section, our goal is by the end of this lesson to be able to look at an equation like that and almost be able to sketch a graph of it without using your calculator, or at least recognize or be able to list certain characteristics of that graph. So what we're going to do right now is part 1b, coming up with the rectangular equation for r equals sine 2 theta. What that means is instead of r equals sine 2 theta, I want something in terms of x's and y's. And we have to recall a little bit of information that we went over last class, because we have to remember how x's and y's relate to r's and thetas. So I'm hoping that by now, after doing your homework last class, that you remember a couple of important relationships. The first one being that y equals r sine theta, and that x equals r cos theta. Those are 2 important relationships. And also that r equals the square root of x squared plus y squared. So those 3 things are going to help us convert this equation, get rid of the r and get rid of the theta, and replace them with x's and y's. Alright, so to get started, instead of this r, well, here's what we're starting with. R equals sine 2 theta. So what we can do, instead of this r, we can write the square root of x squared plus y squared. And we can just use the positive radius for that. So instead of x squared plus y squared, I'm going to write this equals. And now if only I could replace sine 2 theta with something. Well, you're going to have to think way back to first semester, where we learned something called the double angle formulas for sine, cosine, and tangent. And sine 2 theta, we had a formula for, and that was 2 times sine theta cosine theta. So I'm replacing that using the double angle formula. And now I just have sine theta and cosine theta, which I can use these equations to replace, because if y equals r sine theta, that means sine theta equals, if I divide both sides by sine theta right here, that means that equals y over r. And I know that that's hard to see. Sine theta equals y divided by r, and likewise cosine theta equals y divided by, or x divided by r. So now I can write that the square root of x squared plus y squared equals 2 times y over r times x over r. And then we see these r's reappear again, which we don't really want. So we're going to replace, let me write this next line. So just to simplify what we have, x squared plus y squared equals 2y times x over r squared. So this r is an issue because, whoops, r squared. What? Okay. So we've got this, but if r equals the square root of x squared plus y squared, then r squared would just equal x squared plus y squared. So we end up with this equation. 2yx divided by x squared plus y squared. So what we did was we took this polar equation, used the relationships that we learned last class, and some of them that we already knew, and replaced r and the sine theta and cosine theta with x's and y's, and this now is representing the same exact graph, that graph still, but using x's and y's. Now obviously we would have to do a lot more work over here if we wanted to type this into our calculator. We would have several different parts of this graph. Because it isn't a function, we would have to have the positive and negative graphs of it. But it is possible to graph something like that in a rectangular way. However, it's much easier using a nice simple polar equation instead. So this is a case, obviously, where polar just makes more sense. But if you wanted to look at that rectangular equation for it, we can do so. Okay, so that was just converting from polar to rectangular, but instead of converting a single point, we converted an entire graph, equation for a graph. But moving forward, we're just going to focus on what the graphs of these rose curves look like. So using your calculator, again, you're going to need that. Let's go ahead and just change our equation a little bit. Instead of sine 2 theta, we're going to graph cosine 2 theta. So in your y equals, type in r equals cosine 2 theta, and then zoom 5, and take a look at that. Notice that it also has 4 petals, just like sine of 2 theta, but the petals are now kind of straddling each of the axes. So we've got, let's say that's 1. We've got petals looking like that, except better. So we've got 4 petals still, but this time they're actually on the x and y axis. Okay, let's change it a little bit. Notice, I want you guys to just try and analyze the difference between each of the graphs we're looking at. So we changed for number 2, we changed sine to cosine. Now going from what we just graphed to number 3, all we're doing is putting a 3 out front of it. So it's still cosine 2 theta. This time we're just putting a 3 out front of the cosine, and let's see what happens to our graph. Remember, zoom 5. So you see the exact same graph, it's just bigger, and specifically 3 times bigger, which makes sense because we multiplied that function by 3. And the length of the petals are now 3 instead of 1. So I'm hoping you have already begun to pick up on the fact that that number out front is going to tell us the length of each of those petals. Okay, so let's look at number 4, and we see sine of 3 theta right here. So the first graph we did way up here was sine 2 theta. Now we're going to graph sine 3 theta. Now remember, sine of 2 theta had 4 petals. How many petals do you think sine of 3 theta will have? So let's find out. In your y equals, type r equals sine of 3 theta, and graph that, zoom 5, and see what you get. It just has 3 little petals. So we've got, and those are smaller petals than what we just saw. There are 3 of them, looking something like that. So that's sine 3 theta, which what I want you to recognize is that sine of 3 theta had 3 petals, but sine of 2 theta didn't just have 2 petals, it had 4 petals. So that's something that is worth making note of. Alright, let's see what happens when we have cosine of 3 theta. So all we're changing from number 4 to number 5 is the trig function. In number 4, we were looking at this sine of 3 theta. In number 5, we're going to graph the cosine of 3 theta. So type that into your r equals and zoom 5. Again, we see that there are 3 petals. It just looks like it's rotated a little bit. So instead of being symmetric about the y-axis, which number 4 was. Now we have cosine 3 theta is symmetric about the x-axis, which should make sense at least a little bit. Let's graph this first and then I'll explain. I have a hard time graphing these, so with one movement of my pencil. Okay, so we see a petal length of 1 right here. It goes out to 1. And we see that cosine 3 theta is symmetric about the x-axis. And I want you guys to always remember this relationship because we already learned that x equals r cosine theta and y equals r sine theta. And that we should always be associating x's and cosine together and y's with sine. So when we see r equals sine 3 theta, visually on a graph, that is typically going to be symmetric about the y-axis because y equals r sine theta. And with number 5, r equals cosine 3 theta, because x equals r cosine 3 theta, or cosine theta, cosine graphs of cosine functions are going to be symmetric about the x-axis. So those are just a couple of important things to notice here with these. Okay, moving on. What I want you to do is pause the video and graph each of these 6 polar graphs. And as you're doing so, I want you to really stop and focus by looking at the equation and thinking, okay, am I looking at sine or cosine? How long do I think those petals are going to be? How many petals do I think they're going to have? And after graphing each of these 6, I want you to think about this last thing. How does changing the value of A and N, so the number out front, A, and N, the number attached to that theta, how are those changing the graphs of the rose curves? Because eventually you're just going to have the equation, and I'm going to ask you what it looks like. So I want you to pause, graph each of these 6, and really pay attention to the relationship between what's happening in the equation and what the graph looks like. And then we'll recap here in a minute. So go ahead and do that on your own. Alright, so here are the very rough sketches of these graphs after you have spent time plugging each one into your calculator. And so what we're going to talk about is the fact that any rose curve has this equation, this form of an equation. R equals some number times the cosine or sine of some multiple of theta. So we have, oh, there we go, a little more space here. So if we answer just this first part, how does changing the value of A affect the equation or the graph of a rose curve? Well, if you look at A, the number out front, here A is 3, and we see that the length of these petals is 3. Here A is 2, and the length of this petal here is 2. A is 4, length of the petal, 4. So that number out front is always going to tell us the length of the petal. So A tells us length of petal. One thing I want to point out before we continue is this equation right here, r equals 3 sine theta, ended up just being a circle, which it might have confused you at first and you're wondering why is that one a circle. But if you notice the difference between that equation and all the other equations is that it's just the sine of theta, not a multiple of theta. Or if you can think of it as being 3 sine 1 theta. Instead of 2 or 3 or 4, you've got the sine of 1 theta, which means think of it as one giant round petal of petal length 3 because that number out front. So really it's a circle with a diameter of 3. So that's why that one was the only one that is a circle. So next we're going to look at how changing n, the multiple of theta, affects the graph of each rose curve. So The tricky thing is with this is it's not consistent for each of these. So on number 6, N was 4, but there were 8 petals. Number 7, there N was 5, and there were 5 petals. So that matches up. Number 8, N was 3, and there were 3 petals. So it looks like in some cases, N tells us the number of petals. We go down to number 9, N is 2, but there are 4 petals, so that one it doesn't fit with. And then number 11, N is 2 again, and there are also 4 petals. So it looks like sometimes the petal length is doubled by N, and sometimes it equals N. And that is the case when N is even, then there are 2 N petals. But when N is odd, there are just that many petals. So if N is 3, there are 3 petals. But if N is 4, there will be 8 petals. So that's how you can determine petal length, which is that number out front. And then to determine the number of petals, it just depends. If N is even, you double it, that's how many petals there are. And if N is odd, it's just that number itself. So that's how you can kind of break apart these equations for rose curves, and you can find so much about the graph before you even plug it into your calculator. Okay, so moving on to the next page. We've seen the graph of rose curves. We've really looked into the graph of rose curves. We're not going to focus too much on spirals, but we do need to at least touch base and talk about what their equations look like and how those graphs behave. So the first thing is you're going to need to change your calculator a little bit. So first of all, we're still in polar mode. It must be in radian mode, and still in polar GC. Our window is going to change a little bit. So we're going to select your window. You're still from 0 to 2 pi with a step of pi 24ths for theta. Your x-min this time, we're going to go from -10 to 10 on the x's and y's just to begin, and then eventually we're going to have to get a wider view of these graphs. So we will change that in a minute, but right now just change your x's and y's to go from -10 to 10. Eventually what we're going to do is change this theta, our min and max of theta. We're going to change our max of theta in a minute to 4 pi and then again to 6 pi and see what keeps happening to these graphs. Alright, so if we look at our first equation, type into your y equals just theta plus 1. So no sines or cosines, we're just talking about theta plus a number. So theta plus 1, and then remember to hit zoom 5. And what you see, it kind of looks like a shell almost, or the beginning of a spiral. So we've got, let's label my axes here. Go ahead and label your axes. And then the function, or the graph, I keep saying function. It looks like if you look really closely, it might start at 1. And then it goes up a little bit, just slightly above 2. And then almost out to -4. So that's what we get for our first graph of theta plus 1. Let's see what happens. What I want to do now is go back to your window and change the theta max to 4 pi. And then hit zoom 5 again. You're going to see that our graph continued. It continued going around like that, except better. And if you continued again, if you made theta max even larger, say you made it 6 pi, go ahead and do that and hit zoom 5. that spiral is going to continue again, another rotation all the way around. So these graphs, depending on your limitations on theta, but if theta isn't limited and theta can go from 0 to infinity, you see just a giant spiral. So that's pretty cool. One thing I want you to notice about these spirals, I forgot to even mention what they're called. Way to go. These are spirals of Archimedes. Archimedes was a mathematician and apparently discovered these spirals. I will call them Archimedean spirals or arc spirals just because I don't want to write that down. Archimedean spirals always have the same length between each of the spirals. So the length between, like from here, let me change colors. The length between spirals is always going to be the same for each new layer of the spiral. So they're consistent. And the way to calculate that distance between spirals is, it is 2 pi times the absolute value of A. So that's the formula for distance of spirals. It's really the only thing you're going to need to be able to remember from anything about Archimedean spirals, other than the fact that this is their equation. R equals some multiple of theta plus a number. So some multiple of theta, 1 plus 1. And then, so that's 2 pi A. 2 pi times the absolute value of A, which is that number out front of theta. So if we look at the second one, number 7, and plug that into your R equals 2 theta plus 3, and zoom 5. So right away you can see that spiral is much larger than our first one. We don't get quite as much of a complete picture. But let's just see what we can graph of that so far. One thing to make note of is the starting point of that spiral and how that relates to the equation. So looking at your calculator, we can see that that starting point is at x equals 3. And that comes from the fact that it's 2 theta plus 3. And then this spiral is a little larger, and that's affected by that 2 in front of theta. So we won't get to see nearly as much of this one because of how large it is. But if you zoom out, just hit the zoom button on your calculator and hit out and then hit equals, and you get a much better picture of what that spiral looks like, especially with theta going up to 6 pi. And then the distance between spirals, again, this distance between the spirals is 2 pi times A. So 2 pi times the absolute value of A, which is 2. So the distance between these spirals is always going to be a consistent 4 pi. So again, we're not going to spend a ton of time looking at spirals other than I want you to be able to recognize the equation of a spiral, an Archimedean spiral. It is a multiple of theta plus some number. And then also, I'm going to want you to be able to tell me the distance between the spirals, which is just 2 pi times A, that number in front of theta. So, for example, we have just two equations down here. And for Archimedean spirals, first of all, I'm hoping again that in the future you'll be able to look at this and tell me that's an Archimedean spiral. This 2 right here tells us that it has a starting point at x equals 2. So it has a starting point of 2, 0. The distance between the two, between each set of spirals is going to be 2 pi A, absolute value of A. So 2 pi times absolute value of negative 2. So the distance between spirals on that spiral is 4 pi. So if we look at part B, and we've got R equals 3 theta plus 3. The starting point is given to us by that plus 3 at the end. So that means it starts at x equals 3 or 3, 0. And the distance between spirals is 2 pi times the absolute value of A, or 2 pi times 3, which is 6 pi. So that's as much as we're going to delve into Archimedean spirals. Just understand that Archimedean spirals are consistent when you look at the distance between spirals. Their equations always look like some multiple of theta plus a number, and the distance between those spirals is 2 pi A. So that's it with Archimedean spirals. Let's look at the next page at a different kind of spiral. And these spirals are called logarithmic spirals. And if you remember, logarithms are just inverses of exponents. So they're kind of like exponents. And if you look at the equation, you see that our theta, our variable, is in the exponent. That's why that's going to form a logarithmic spiral. So you do need to change your calculator just slightly by going into the mode or the window and notice our limitations on x and y. So we are going to be looking at a big picture of this logarithmic spiral because just like exponential and logarithmic functions, logarithmic spirals grow very large very fast. So our x's are going to go from negative 1,000 to 1,000 with a step of 100, just so it's not taking forever to graph. To 1,000. Okay, so change your window here, and then in your y equals, just type in 2 raised to the theta, and remember to hit zoom 5. Okay, so even with going out to 1,000, so if each of those little lines I just marked equal 100, I'm still not getting much of this spiral at all. So you're going to see the spiral starts really close down to the origin. We can't tell exactly because we're zoomed out so far, but it just gets so large we don't even know what the rest of that function looks like, or that spiral looks like. Actually, okay, I'm not good at drawing these apparently. Okay, you get the idea. Look at your calculator, and what we can do to help us zoom out, or to view this a little better, is zoom out. And you'll see that this just continues. It gets so large so fast we can't even see it spiral around one full time, hardly spiral around one full time. So logarithmic spirals get very large very, very fast. We're not going to dive into them too much. All you need to be able to do is really look at this equation and tell me that that's going to produce a graph of a logarithmic spiral. So we have our two spirals, Archimedean spirals, which look like this. So arc spirals look like some multiple of theta plus a number. But then logarithmic spirals are equal some number raised to the theta. And there's not a ton of information you need to be able to know, especially about logarithmic spirals, but we definitely just wanted to see what those graphs looked like. Okay, so that's it for graphs of rose curves and logarithmic spirals. If you look onto the next page, you see this review of polar equations. We will save this for in class for when I'm there with you. And if you just look at each of these names, limicon, cardioid, we haven't even talked about. It's a special type of limicon, but we will talk about that together. Circle, rose curve, spiral of Archimedes, and logarithmic spiral. So those are the main 6 graphs that we're going to be talking about and learning, and kind of, I want you guys to be able to recognize which equations produce which graphs. But we will kind of review all of these together next class when I see you on Wednesday. Okay.